you remove that edge, and then you add some new small structures or new subgraph at that edge. So we take this idea in our optimization process. We first predict something called a disconnection site, but you can just consider that as a bound or as an edge in the graph, as a bound in the molecule. And we modify the molecule by changing the fragment at that site. So by doing this, we can retain the majority of the molecular structure and only change one small fragment at disconnection site. And the next question is how to change. This will be some learning things going on. So we learn from the difference between molecules before and after the optimization at one disconnection site. So the idea is in our training set, we have molecules that are modified from another molecule, and we know where the modification happened. So we use those molecules as our training set. And we learn the difference between the molecules, the before and after molecules. When we generate new molecules or when we modify the molecules, we want to generate only one fragment that can kind of instantiates the expected difference. So I'll talk about that later. So this is about our embedding the latent space thing. And after we generate that fragment, we just remove the original fragment at disconnection site and add the new fragment at disconnection site. So this is about just one fragment at one disconnection site. But if we do multiple sampling from the latent space, we can generate multiple different fragments. And from there, we can modify the molecule in different ways. And if we just pipeline all such generation modules, and if each module modifies just one disconnection site, then multiple molecules in the pipeline can modify multiple disconnection sites of a same molecule. So that's how we can implement the multiple disconnect site modification. So this is the whole idea. And in terms of the problem definition, I hope it becomes clear now. So the idea is giving a molecule Mx, we represent the Mx as a graph structure, and we want to modify that graph structure into another molecule My such that the new molecule is similar to the initial molecule. So we will have a similarity threshold to make sure that structure-wise, the new molecule is still similar to the old molecule. But we have another property constraint, that is the new molecule has better properties. And you can define what kind of properties you want to implement. It could be just one property or multiple properties together. So that's the problem. So this figure just shows the overall structure of our Modif one fragment-based generative model for molecule optimization. So again, this is a encoding decoding framework. So in the encoder part, we want to learn quote unquote the rules or the typical ways to modify one molecule into another molecule. So in the encoder, the training instance, each training instance is actually a pair of molecules or a pair of molecular graphs like this, as an example here. So these two molecules in the same pair are very similar. Like for example, in this case, these two molecule graphs are very similar. The only difference happens at this carbonate atom. So in the first molecule, it's connected to a nitrogen atom, and in the second one, it's connected to a ring. So structure-wise, they are only different at one particular atom, one particular location. Actually, that location is our disconnection site. And in terms of properties, the second molecule has better properties. So in our development, in our algorithm, we target a particular property called log P, which measures the hydrophobicity of molecules. But you can just plug in whatever properties you want to improve. But the idea is these two graphs are very similar and only different at one particular atom, and one molecule has a better property than the other molecule. It's not necessary that the larger molecule has a better property. It's possible that the small molecule has a better property. doesn't really matter. As long as there is a property difference, there is a small structure difference among these two molecules. And we learned the difference of this quote-unquote difference of these two molecules and embed the difference in our latent space. And in the decoder part, we want to change a given molecule, and we just sample from the latent space, and you can consider that as to sample a kind of a rule, modification rule, and based on that rule, we add, we find the disconnection side, add atoms, and grow that molecule into another different molecule. So that's the overall idea of this framework. So let's look at the encoder part first. So again, as I mentioned, in the encoder, each training instance is a pair of graphs. And for graphs, then we want to use graphs, then there must be some representation things, some ways to represent the graph and represent the information in the graph. So in our case, we have the graph, it's the typical graph representation for a small molecule. We also have its corresponding another representation called the junction tree. Actually, it's also a very well-developed concept. But the idea here is each bond in the molecular graph becomes a node in the junction tree. And if two bonds share a common atom, then the corresponding two nodes in the junction tree will have an edge in between. So that's how we convert bonds to nodes and convert the common atom into edges into nodes, and from there we generate a tree representation. So particularly for the rings in the molecular graphs, each ring become a certain node. So the color here represents the correspondence between the graph and tree. So this aromatic ring here, the orange one, this ring becomes a certain node in the tree. So by doing this, we convert a graph into a tree, and we always like trees better than graphs because no cycles and easy to represent a lot of good stuff about trees. So the first step in our decoder is to represent the information, represent the structures of the molecule. So we first use the graph message passing neural networks. It's a graph convolution neural network over the graph representation. So this is just to learn the atom to represent the atom by leveraging its neighborhood structures in the small graphs, in the molecule graphs. And we do a very similar thing over the junction tree using tree message passing neural network in order to represent the nodes in the tree by somehow intuitively by looking at the local and the global structure of this tree. So from there, we can represent each atom in the graphs, and actually those atom embeddings, atom representations are used in the tree message passing in order to represent the nodes in the tree. And as we can tell, among these graphs, actually the difference of these graphs and actually the difference of their corresponding junction trees is only at this blue node. So in the first tree, the blue node is connected to a purple node and these bigger structures. And in the second tree, this blue node, dark blue node, is connected to another different nodes and the same structures here. So the difference between these two molecules or between their corresponding junction trees is only at this particular blue node. So we think the difference at that blue node should tell us how to modify the first graph into the second graph. So that's how we come up with something called the difference embedding. So we represent the first dark blue node in the first tree using its own embedding and the embedding of this purple node or the embedding of the different substructure in the first tree. Similarly, in the second junction tree, we represent the blue node using its own representation, the blue embeddings here, and also the other two nodes, other two different nodes connected to this blue node. So correspondingly, this is the green embedding and light blue, sky blue embedding. So we calculate the difference between the H minus and H plus representation of these two molecules, and that gives us the difference, quote unquote, difference of these two molecules. And we embed the difference into a latent space following the normal distribution. So this is the encoding phase. So again, you can interpret this encoding phase as to learn the kind of rules in order to change one molecule into another molecule, and the latent space just embed those rules. Then let's look at the decoder part. Oh, sorry, it's a decoder. It's a decoder, not encoder. It's a typo here. So in the decoding part, we want to leverage the rules that we just learned from our training instances and use those rules to change one molecule into another molecule. So we start with a molecule that we want to change, want to modify. So the first phase or first thing to do is to predict where the disconnection site is, or in other words, where we should change at this molecule. So here in the first figure here, we represent the molecule that we want to modify using its junction tree. And for each node in the junction tree, we do the disconnection site prediction. And in order to do the prediction, we first sample a embedding from the embedding space, or intuitively, or just sample what kind of rules we need to apply here. And we also use the embedding of the node. For example, we're looking at this dark blue node here. So we also use the embedding of that dark blue node in order to do the prediction. So the idea is to predict where the disconnection site is. We need to look at what kind of chemical rules we need to use to do the modification, and we need to look at the content or context of this node that we want to predict. So let's say if we predict that this blue node is the disconnection site, then the second step is to predict which fragment connected to this node should be removed. So for this particular node, in this case, we have two fragments connected to that node. The first one is connected through the orange node here. The other one is through the purple node here. So for these two nodes, we predict whether we should remove them or not. So for example, to predict if the purple node should be removed, we use its embedding, embedding, the purple embedding, and also we use Z minus. So Z minus is sampled from the latent space. It represents quote unquote the smaller molecule, or it represents the molecule, it corresponds to the molecule after the fragment is removed. So we use these two embeddings together to predict whether these molecules, this atom should be removed, or the fragment connected at this atom should be removed or not. So that's the removal fragment prediction step. So let's say we predict that this purple node should be removed, and then we remove that purple node. After we remove the purple node, we can generate something called intermediate representation. It's going to be the remaining junction tree and the corresponding molecular graph. We can map the tree back to the molecular graph. So they are intermediate representation, meaning that they are not really valid chemical compounds. They may have some charge, or they are not really stable. They are not really valid. They are not the final product. And from there, we want to add some new fragments to the intermediate representation so as to grow it to some valid and better molecules. So the idea here is, first we predict whether the disconnection site should have some new atoms attached. See, here we call it a new fragment attachment prediction. So remember, the dark blue node here is our disconnection site. We just remove the fragment from there. So next, we want to predict whether we should add something back to the to that disconnection site. And let's say if we need to, so it's possible that in the end, the prediction says, no, we don't need to add anything back. And then that's it, we just stop there. Otherwise, if it says we need to add some new fragment, then the next thing is, the first prediction is called child connection prediction, whether we should connect some new atoms at the disconnection site. So those new atoms are the the children of that disconnection site. And after that, we need to, so if it says we need to add some new atoms, then the next step is what kind of atoms to add, or
looks like we lost Shia. Maybe she's gonna come back. Am I the only one that lost the presentation, or?
No, same for me.
Okay, well, that's the joy of online online
It was
presentation.
good while it lasted.
Yeah, it's quite different from our usual talks, and quite interesting. I mean, while she's coming back, yeah, I when I was a postdoc, I worked a lot on what we used to call graph learning. Oh,
I'm sorry. I think something
Hi, Shia, welcome back.
Sorry, something wrong with the weather and with my power at home. I don't know. Anyways, but I'm back. Let's see where I was. So I think I was here, right?
Yeah, exactly.
Yeah. So then we need to predict the atoms, I mean, the type of atoms that need to be added at this connection site. And the prediction is going to be based on the current, the atom that the new atom needs to be connected to, and also the current tree structures. And in the end, we need to predict exactly the attachment point. The reason for this prediction is actually particularly for the rings. If it's a single bond or a trivial bond, then it's easy. But if the node in the junction tree corresponds to a ring, then we need to predict which atom along the ring should be the attachment point. So some additional predictions, particularly for rings. And in the end, we always check whether our prediction is valid based on chemical rules. For example, based on bond types, whether we can add a certain atom if there is a double bond or if it only requires a triple bond. So those valence checking to make sure that everything is chemically valid. So we do this iteratively until the child connection prediction says we need to stop. So that's how we add one atom at a time until the iteration stops. And from there, we can map the junction tree back into its corresponding molecular graph. So that's the decoding part. So I hope this this overall structure, overall architecture is clear to you. So just let me know if you have any questions. Okay. Then I want to show you some experimental results and also some conclusions.
I have one question. Sure. I would like to know what specifically are the at any point what specifically are the inputs and the outputs of the algorithm and the molecules.
Sure.
Thanks.
Yes. So this is the overall structure. So in the training phase, the inputs to the model. I mean, in the training part, the inputs will be the training instances, right? And each training instance is a pair of molecules. And so for the encoding, I mean, we learn embeddings from each pair of molecules, and to train the decoder, it's still a pair of molecule. It's just we want to modify one of the input molecule, one of the molecules which have worse property into the other molecule in this pair, which has the better property.
Okay, thanks. And for the output, is there the idea that you can add various types of potential molecules that you could add on, and so you'll add on a bunch of candidates and find the most probable?
Yes, yes, we can do that. And actually, that's exactly what we did. So remember, to decode to change a modified molecule into a better one in the decoder phase, we need to sample from the latent space, right? So if you do multiple samplings, then you can decode a same molecule into different outputs. And some outputs may have better properties, then you can search for the best one among all the decoded molecules.
Okay, thanks.
Sure, thank you. So let's look at some experiments to give you a quick idea about how the experiments are done. So our training set is again a set of has all the molecule pairs. So in the end, we have about 56K molecule pairs which satisfy those properties, like only different at one disconnection site, and one has a better property than the other one. So we can identify about 56K training instances, and all the other statistics here just to give you some ideas about the properties and size of those molecules. And this figure shows probably the overall results of different methods and the comparison. And so the last two rows correspond to our methods. I mean, actually, it's the pipeline of identical modules, and each module can change at one disconnection site of a molecule. And the first 6 methods are actually the kind of state-of-the-art method in literature. And probably, as you can imagine, some methods are based on fully encoding decoding, like JTAVE. This is a VE-based encoding decoding method. It encodes the entire junction tree and decodes the entire junction tree from the latent space. And some methods are based on graph flow. So last graph AF and mole flow, these are the 2 methods based on graph flow. So basically, it's a invertible mapping between the input graph structure to a latent distribution, Gaussian distribution or some distribution, but it's invertible. So from that distribution, you can invert the encoding part to generate a molecule. And also, as you already imagined, there are reinforcement-based method. The graph AE also applies reinforcement learning, like graph AE and GCPE is also a policy network. So they learn how to add atom, and after you add atoms, there will be some final reward, and the reward is the property. So there could be they design the reinforcement learning framework in order to change and to add new atoms and new bonds. And our methods is different in the sense that we learn from the differences of molecules, and we can retain this. We don't really decode the molecules from the latent space, but we change an existing molecule gradually. And we look at the performance of this method based on different similarity constraints. So for example, if we don't really require that the decoded or the modified new molecule is similar to the previous molecule, to the initial molecule, then you can imagine in terms of property improvement, we can improve really a lot, because we can generate whatever molecule, whatever structures you want, as the property can be significantly improved. But if we have some constraints on the similarity, for example, 0.6, actually 0.6 is a very high similarity constraint, very strong similarity constraints between the molecule before and after the modification. And in that case, actually our method still significantly outperform the state-of-the-art method. It's like we can significantly improve the performance, but at the same time, we make sure that our the modified molecules are still very similar to the initial molecule. We believe this is what really needed in practice, because for a molecule, after we do the screening, we identify some promising molecules, and suddenly after we generate molecules, it's different structures. So that doesn't make a lot of sense in practice. So we believe by doing this, our method can very much approximate the real bench work and real modification in drug discovery, and still retain the major scaffold, the major structure of small molecules. So these are the kind of very high level comparison and analysis of a method with and comparison with the existing method. And actually, we also did some other analysis about, for example, the model complexity, and it turns out our model is much less complex compared to all the existing methods. We have actually fewer parameters, and we don't need, I mean, our training set is actually smaller than the training set of all the other methods. I mean, the testing set is always the same, but our training set is much smaller. So we believe there are some very strong good points about our method in terms of the performance, in terms of the training, in terms of the interpretability, because I mean, it's very easy to, it's easier to understand or to control what's happening in the pipeline, and to somehow, if you want to stop early in the pipeline in order to maintain a high similarity, you can do that. You have some control over the pipelines in terms of how to modify different disconnection sites, or how to maintain a high or low similarities among the molecules. So that's the overall performance in terms of the property improvement. And here I want to show some case studies or some instances about what we really did here did in our experiments in our model. So some popular some fragments that are kind of popular to be removed from the molecule in terms of the in order to do modification, and some fragments that are typically added to the molecule in order to improve the property. So we actually have two chemists who helped us to interpret these fragments, and they can identify the corresponding chemical rules, and showing that this type of removal and attachment is actually meaningful in order to improve the properties. And I also want to show you an example about the modification that that our model did. So for example, we want to modify this molecule, and it's the initial molecule to molecule to start with, and this -5 is the property. So the first step in our is actually our method add a new bond, change the atom and add a new bond here. So the red highlighted fragment is the new fragment that has been changed or added to this molecule. And by adding this red bond, the property is increased to -2.6. And in the third step, another ring is kind of inserted or added on the right-hand side, and that increases the property to -0.7. And then actually it's another aromatic ring here added, and that's continues the increase of the property. And later on there is so this is another 2 bonds added to this aromatic ring, and in the last step another bond is added to another branch, another bond at this ring. So this is just to show how our it's just to give you a example about how this molecule is modified into another one, and actually our method does all the modification in a very end-to-end fashion, and it's purely data driven. We didn't really impose any chemical rules or chemical knowledge in our learning process. And also, as I just mentioned earlier, our method can also do the multi-disconnection site modification. In the first example, it seems that all the modification happens at the kind of right side of this molecule, but we can modify multiple different places, through a pipeline. So for example, we start with this molecule, and in the first step, we just change the fragment on the left-hand side into another ring. And then some small fragment are added at this ring. And later on, the modification happens on the other side of this molecule, like another small bond is added to this to the right kind of branch of this molecule. And in the next step, another small fragment is added. And in the last step, actually, it goes back to the left side of this molecule and add a different bond there. So as you can tell, the modifications happened at different places of a same molecule. That's why by modifying one fragment each time and pipelining all such modification, we can modify a molecule at different sites, different places. So I believe this is the experiments that I want to present. And here, just to give you a quick list of all the references, including our method and including some baseline method. And this is a very recent paper. And in addition to the full manuscript, actually, we have about 20 pages of supplementary materials. And I do suggest that if you're interested, go over the supplementary materials, because we talked about many different things, including reproducibility, including how to measure graph similarities, including experimental comparison, like many methods that report their results, but they use a different data set, not the benchmark data set, but they compare their results against the results over the benchmark data set. And also there are issues about reinforcement learning, like during the testing phase, they apply reinforcement learning, and we think there is an issue there. So many issues or many discussions are included in our supplementary materials, and the code is available online. So again, if you're interested, please play with our code. And I believe that's the end. And I'd like to take any questions if you have.
Michael, I think you had a question first.
Yes, so thank you very much for the talk. Very clearly explained, but unfortunately, I am not a machine learning person, so there's some basic things I did not understand. If you go to slide 17, you were showing us some example sequences of optimizations or improvements.
Oh, I see.
Yeah, here. So the property here that we see going up and up and up, is this the hydrophobicity you mentioned earlier?
In this case, it's hydrophobicity plus accessibility or synthesis accessibility plus ring size. It's not only one.
And are these values computed or they're measured in a wet lab?
And that's a good question. That's the question we got from our review. It's computed. We didn't really have a way to validate all the results in the wet lab. And actually, these computed results have a very high correlation with their ground truth result. So it's very close. So that's why we use the predict or computed values.
So I want to check that I understand your work. So your machine learning model predicts how to modify the molecule. And then you have another algorithm which computes these numbers we see, and that second algorithm, maybe that's like previous work done by other people, and it's highly correlated with what we'd measure in a wet lab. Is that right?
Yes. So the properties are calculated using standalone third-party algorithms, which have been very well validated, and we use their result as a way to measure the property of our molecules, our modification. Okay.
So another question is, do you have any interest in molecular dynamic simulations or simulating the motion, the folding of molecules? Could that be interesting maybe for generating training data or for evaluating predictions of machine learning?
And that's a great question. Actually, very recently, in the last probably 2 or 3 months, there have been papers published on AI for dynamic modeling for 3D structure estimation of molecules, like the binding mode, those type of things. And yes, we do have interest on that, and we have some work very related work going on. It's not on molecules, but on peptides. So we want to leverage a physical model as a way in our training process. I mean, in that piece of work, we used physical models as a way to give us a reward in the reinforcement learning framework. But here, I think your idea is just great. I mean, we do have the issue about the training data. This is because, I mean, of course, we want to use more training data, the larger the better. And the second thing is, remember, we construct our training pairs based on the properties that we want to optimize. So now we optimize, I believe, 4 or 5, we can optimize 4 or 5 different properties at the same time. But as you can think, I mean, the more optimized that we want to optimize at the same time, the more constraint we have our data set, because each pair has to satisfy all those constraints at the same time. So we'll have a smaller training data. So if there are ways to generate more training data, that could be great for us. I mean, that could solve a lot of issues in our training process. And also, even I believe even in the modification process, there is room to leverage chemical rules, physical models even in the training process, not only for the training data generation, but in the training process. So that's something that we have been thinking about. So definitely, I think that's a very interesting perspective and a very interesting idea.
Okay, so the reason I thought of that idea is because maybe you've seen these depth cameras, the Microsoft has this Xbox with the Kinect, and it can see your hands and your body, and the HoloLens is a headset that can see your hands. And I remember reading that the way they trained their machine learning algorithm is they generated synthetic data sets with using 3D model of hands, putting it in many different poses, converting those to images, and then training with that. So, okay, very interesting. Thank you.
Thank you.
Thanks, Michael. So we have time for maybe 1 or 2 questions. Anyone else? I have a question. So yeah, the talk was really interesting. My question is, so you're basically you use a stochastic method to generate the new molecules.
Yes.
Is there a trade-off between like coverage? Like obviously a stochastic method might not generate all the possible molecules. Have you tried to measure the coverage compared to a more deterministic exhaustive search kind of approach?
Oh yeah, that's a great question. I believe in our supplementary materials, we have some analysis about the coverage. Like, I mean, if you think about the entire space of chemical compounds, that's an entire space, and we can generate some molecules. And if you locate those molecules in the entire space and compare where they are with respect to the particularly the drugs, the FDA-approved drugs. So we had some analysis about that. But I understand why you asked that question. So it's always a limitation about this type of work, and even generative type of modeling and also reinforcement learning model is about exploration towards something that is not really included in your training data. So in our current work, we don't really have a mechanism to do that. We don't have a mechanism to go, I mean, intuitively to go beyond what is included in our training data. We don't really have that, but definitely I agree with you. That's a very, very important question. I mean, I don't know if it's easy to address, but definitely it's an important question.
All right, maybe one last question from someone else. No one. So maybe I have one last question. I just want to confirm: is the whole everything is differentiable in your model?
Yes.
Okay. So those properties that Michael was asking about, and you said you were using a model to predict. So these are differentiable models, or do you use some sort of a reinforcement kind of trick to make it differentiable? Or
Wow. Okay. So actually, I I didn't really show our objective function here. So in our objective function, we only care about whether the property is improved or not. We don't really care about the values. It's just better or not. And we can make that differentiable.
I see. Okay, so you can make it differentiable without having to, let's say, run a simulation or some sort of a complex. I see.
Right. Exactly.
Great. Well, let's thank the speaker for the great talk and the availability. So, thank you.
Thank you.
Always.
Thanks a lot.
Thank you.
Thanks for the great talk.
Could I ask one more quick question?
Sure.
So if someone is interested in this area of molecular biology or molecules and computing, can you recommend maybe a book or a course or something that someone could take to learn more?
You're talking about the general like AI for biology, for chemistry, or this particular problem, like
even not necessarily AI. Like my background's in computer science, but I'm interested in molecular biology and I'm interested in the types of things that you're doing, but I don't have enough background to understand all the details. And machine learning, there's lots of resources I know about for machine learning.
Yes, probably I can think of some references for you. But what I know is never on on the computer science AI part, they are not really very in depth. So it's a kind of combination of AI and biology, chemistry, and they do have some basic chemistry and dynamics, those type of things. So I can definitely find identify some references for you.
Okay, thank you.
And also docking physical simulation from there.
Thanks. Well, thanks again, Xia, for the great talk. And obviously, if you ever come to Montreal for a conference or other purposes, feel free to drop me a message and I'll be glad to show you around.
Oh, thank you. Thank you for saying that. I really hope that we can travel very soon.
Yeah. All right. So, well, thanks again. And yeah, keep me informed of if you have any other work that you want to present. It's going to be a pleasure to have you again.
Thank you. Thank you for having me. Thank you.
Thanks. Okay. Bye, everyone.
Bye.
Bye.